I'm Çağatay, a real difficult Turkish name. Sorry about it. I live on that red note where you see on the northern Sweden, where it's really cold, and there is a climate positive grid. Let's say it is a really flourishing environment for data centers. Uh, so I'm a physicist, a raster physicist per se. This is more or less present in the sustainability side of my studies, and then I continued my studies with marketing department, where I focused on the effect on open source and open innovation in the data center market. And in the last 3 years, besides, as Manolis mentioned, my responsibilities in Open Compute project, last 3 years I'm a project manager at RISE. RISE is a big research organization owned by the Swedish government. We are too big, but my computer science department, obviously, it is also quite big. The ICE data center and scalable system units, which are located in Luleå, up north Sweden. We are focused on technology validation, and we are also trying to tackle the heterogeneous compute management issues. Today, I will try to focus mostly on technology validation. I will try to, informally address you what's happening in this domain. We are here because the European vision of, digital sovereignty. I would separate data sovereignty and digital sovereignty, because for me, digital sovereignty it is a really bloody environment where we have to compete with global actors. And the vision of having the European chips, it is on the core of that. We believe it's really important. And the progress of this initiative is bringing us to a stage where this European technology, European chips, they have to be demonstrated in systems, in heterogeneous systems, to be precise. So this is where mostly our units are stepping in, where we are trying to understand these technologies, test them, and validate them. So according to AI, validation, it can be actually named under different ways, but in simple ways, it is a process of proving the technology in real life-like environments to make sure that if the technology hits the market, it's ready, 100% ready to perform and cover the needs of the market. There were multiple stages, of course, like prototyping, testing, and different technology readiness level steps that I will talk a bit more in the next slides. But what is really important, down you see actually how technologies are pushed to the market. We are trying to, if you ask me the marketing chat, with the marketing head, I would just say none of these technologies which are reaching early maturity actually survives. If you reach early maturity, then this technology starts making you money. But this is really risky process because at the beginning of this phase, in the design phase of your product, usually you spend a lot of money and time, and if your product is not meeting the market requirements, if it is too early or if it is too late, then it's a big risk when it comes to market penetration. And this risk, I want to give you some examples, and these are actually two bad examples, but we have taken a lot of great lessons from them. So I want to see the full size of the glass. One of them is about these numbers. Maybe some of you might recognize this flow. It was actually coming from some early days of the Pentium processors. There was a flow in the floating point unit. And at the end of the day, one teacher identified that. As you see on the top, the calculations were quite accurate, but after the fourth element in the decimals, it started giving wrong calculations. This small issue in the product cost like half $500 million to Intel back in the day. It is unadjusted for the inflations and so on. Another example, it is more on the hardware side. This was one of my phones that I loved using it. Then I had to change it twice. And still I couldn't use the phone because the faulty implementation of the batteries The phones, if you probably you remember, they were catching fire or exploding, and I wasn't even able to fly for a few times because of these risks. And it cost more than $5 billion to Samsung, according to internet. So even these two examples, I think, simply explains why it is really important to take any necessary stages to, in a controlled way, increase the products or innovations technology readiness level step by step in the right environments. What they do, what big organizations do, like the giant ones like Microsoft, Google, Amazon, Meta, Apple, they spend a big percentage of their revenue to their R&D practices. It is not only like digital companies. You see, the leadership is on the pharmaceuticals. Then it is coming with another technology and software companies and the market giants. And all together, they are trying to make sure. You see the other colors on the down, there is a significant gap, which shows us one thing. There are some innovations, some market segmentation, like digital technologies, like medicine and so on. It is really critical. Like we have to pay a bit more attention on testing and validating these technologies before we present them to market, because the results can be, the consequences can be drastic. So what I'm talking about, usually in the European Union and in the innovation projects under European Union, we talk with technology readiness levels. I actually put some examples here, but the previous presentations also demonstrated it really well, like how European technologies are being tested in lower technology readiness levels. So the first step is basically after the proof of concept, we try to validate the technologies in the laboratories, and then we take them to relevant environments which replicate the real environment. And usually these projects are research and innovation projects. And then once the technology is validated in a relevant environment, we actually support it until this system prototype is demonstrated in an operational environment. So this two-stage actually allows us to securely increase the technology readiness level and market readiness. I really like this example. Again, thanks to AI. Many people, they don't know that Einstein got actually a Nobel, not with relativity, but photoelectric incident. But many also of us, we don't know. It was more than 100 years ago that Einstein explained the duality of the light, the particle and wave duality. What I'm trying to say, this concept actually enabled all these photovoltaic technologies in the market today. And even today, with the flexible products that we use in the market, each time we introduce a new PV technology to the market, we basically use the same principles. Low TRL technologies observed 100 years ago, but each time we improve the product, we actually lower the technology readiness level, test it again, and present it to market again in a safe way. So if we come back to data centers and our topic today, we actually use a similar way. We use the same technology readiness level ratio. Giving you an example, relevant environments. This is one of the test beds, only one of the test beds that we have. I wanted to show you, demonstrate you how we think, how we work. So once a server prototype, any IT prototype is ready, it is just an example. We take it and we put it in, this is an air-cooled test bed. There are also, liquid-cooled test beds and so on. We take it and we put it in our testing environment. This is equal to TRL5. And in this environment, we actually, this whole test bed has multiple sensors, which allows us to run the IT in a really controlled way. The pressure differences, temperatures, airflows, everything is precisely being controlled and recorded. So what it allows us, it allows us to record everything about the environment, and moreover, I think more importantly, every effect of this environment on the IT system itself. If you see my colleague John Summers is holding the server, this is an OCP server, and on this server there are multiple sensors which are giving us critical data. And most of this data is being used by the operating system and the board management system, and then it's mostly going to trash, not being utilized. So we also collect this data and make it useful. Let me demonstrate it how it works. We get this big data, and we step by step process this data and turn it into something useful. For example, this example is giving you the CPU frequencies. First visual, it wasn't giving us mostly anything. And the second visual, we started understanding different workloads effect on the CPU frequencies. But moreover, it is also explaining us how temperatures are affecting the frequency. So it is more or less allowing us to detect thermal throttles in the system, and helps us to understand if we can detect poorly cooled servers and if we can affect let's say poorly performed IT, managed IT. So this is as discussed around technology readiness level 5. This is a public report of us with Nexulus. Step by step, we understand the performance of the product. We simulate it if necessary, like you see on the CFD results on the right. And we can also compare it with the market, let's say other products in the market, and see how it is positioned. Also, we can understand at this stage if this product is complying with the standards. Like giving an example, if we put it in a real life-like environment, in a place in a data center, and if we actually cool it differently, if this IT is performing in the right way, according to different classifications of ASHRAE standards. So after this stage, actually, things are getting a bit more complicated, because we are starting thinking about having some clusters of IT and how we can actually make them useful for the society. This is a graph which is describing the compute demand when we are training the foundation models and large language models. I think this is one of the really critical parts in the history, then like a paradigm shift, I would say. We started using, which is highly relevant to RISC-V and higher projects as well. We are actually seeing a big demand in the data center environment. The customers, they want more and more powerful systems to aid the models. This incremental growth has to be supplied, and during this supply, if we also see the performance of the hardware, we started seeing a gap in between demand and supply. And in most of the events, especially in open compute and so on, this gap is something that we try to address, and all these innovation projects that we mentioned, they are going to be critical for the future of Europe. So the observation is compute hardware supply is rising, but it is not going as fast as the demand, and it is actually taking us to another step of the technology validation, where we try to provide the right power and cooling to clusters. And this is a project, again, mainly aided by the OCP environments. And we try to start thinking about 1 megawatt IT power on a single rack. Just for you to know, 10 years ago, we were talking about an average of 8 kilowatts, and the jump is about to be to 1 megawatt. So it is introducing big obstacles in the market when it comes to power and thermal management. So in the market, we try to find different solutions to validate these technologies. Like we start building chip load emulators, because if you want to try a 1 megawatt rack with a new innovative cooling system, we had to spend maybe hundreds of millions euros to provide that system to us. But we try to develop right technologies to test this system, these technologies, in a relevant environment. And this is not over, of course. This was just an example, one obstacle that we are having. For the rest of the systems, if we want to reach system prototypes demonstrated in an operational environment, then RISC-ICE data centers and different units are actually joining in. And what we do, we have a research data center, the picture that you see, where we can test innovative technologies in a bit more flexible way than operational data centers can do. So most of the things that I have talked until now, it is mostly covering hardware, I know. But with this image, I would like to introduce you a bit more sophisticated environment where we try to test and run not only hardware, but also network technologies. And we also host different infrastructure and platform management systems in our systems. I think I'm proud to say that nearly all the software we use in our facilities are open source. So that's giving us a great flexibility to answer European research environment's needs. And while we are answering all these needs, we also provide like infrastructure, like user experience, like ICE Connect, where you can actually bring your technology, run it with any open source solutions you want. Either if it can be a virtual machine, it can be a container engine, or it can be a bare metal system, of course. And you can ask us to test it and share the results only with you. So this is more or less how we address your needs. Okay, last few slides. Obviously, our scope is not over there. We are also trying to see the bigger environmental effects in the data centers and buildings. And I would say some of the simulations that we do is based on digital twins and advanced simulation technologies, where we are trying to understand for example, heat demand of the buildings and districts, and we try to orchestrate the data centers and IT according to the needs of the environmental variables, like in this case, like external temperatures and its effect on the energy demand on the environment. Okay, what mostly I discussed about hardware and how hardware technologies are demonstrated. Also, as discussed, this is not only about hardware. We are talking about a full compute continuum spanning around AI factories, cloud, and edge. And we also work on technologies and support European ecosystem with technologies like made operating systems. It is as I can be understood in the name. It's a virtual operating system where you can, like you are plugging in a USB-C cable, you can plug any kind of executor in your system. It can be a supercomputer, it can be a cloud, it can be an on-prem or telco edge, or it can be as like lightweight IoT device. What it allows you to to connect your data and train your models anywhere in this heterogeneous compute continuum. And if you don't need any of these elements, you can basically unattach it and introduce another element in the system. As last slide, what I wanted to say, we are actually getting into a more complicated era where we will feel the heterogeneous computing more and more. Especially with the agentic compute continuum, I would say that we will keep on pushing the compute on the edge, where more heterogeneous IT has to be actually entered the market and answer the needs of the modern compute continuum. It will require us to validate these technologies to make sure that European compute continuum will run in a safe manner. Yeah, I think that is all from my slides. Sorry, one last page. I think Manadis already mentioned, and also there are different organizations like Linux Foundation and so on. There are multiple organizations in the world which are contributing to open environment, which is really important. I would like to highlight Open Compute project because when it comes to technology validation, it's really important that customers and technology developers work together on the same open platform and improve accelerate the speed of the product's market entry in the safe way. So if you don't know about it, I strongly recommend you to check Open Compute project, and you feel free to use it in your innovation projects. Okay, I think that's all from my side. Thank you everyone for listening.